Everybody, this lab is really similar to the last lab. So whereas last time you had a ramp and then you put different objects and then it would slide down the ramp. So let's say it would slide some distance d, and then there would be kinetic friction over here, right? And then there's some angle, and you would measure the time, right, it took to slide down the ramp. So this time you're going to find round things and then have them roll down the ramp. So you start at rest and you want to have your objects roll without slipping. Like if you have something round and it just slides, that would be just like the last experiment where that would be kinetic friction. But if it rolls without slipping, that rolling friction is actually static friction. Okay, so what you want to do is you want to find, let's say, 3 to 5 different round objects. So for example, if we look here at this table with different moments of inertia, like a solid ball or a thin spherical shell, so like a hollow ball, or a cylinder, or a disc, or a hoop. So if you could just find 3 different things, that's good, but more is better. Like if you can find 5 different things and just roll them down the ramp, 10 trials, just like last time, and then measure the time, the distance, and the angle, just like last time. So really similar. Let's get to the derivation. If you have a round object rolling, what does the free body diagram look like? So here's the object. So if the ramp is here, then it's in contact with the ramp, which means there's a normal force here, normal to the ramp, if the ramp is like this. Normal force. And then there's friction this way, opposing the motion if it's rolling this way. And that's static friction, if it rolls without slipping. And then there's weight acting at the center of mass of your object. Okay, and then if it's rolling this way, if I pick coordinates, say this way, it's accelerating this way. So pick my coordinate axis in that direction. And then let's say I'll pick y so that z is this way in the direction that it's rolling. So that means y would have to be this way. Right? If x is here, y is here, z would be out of the page, because this cross this would be out of the page, which is counterclockwise. So I picked it like that because the linear acceleration is in the x direction, but the angular acceleration is in the z direction. Okay, so let's write Newton's laws. So for rotation, some torque about this center of mass is, so the torque by this force about this point is 0. The torque by this force about this point is 0. The torque by this force, this is the lever arm here, R times Fs. And then they're 90 degrees, so then that's it. And that's going to go this way in the positive z direction. So there we go. Equals I alpha. So that's the moment of inertia of your object about the center of mass. And that's the angular acceleration. Okay, now let's sum forces in the x direction. So x is here, and let's see, if the angle is here, then that means theta is here. So that would be mg sine minus direction equals mass times acceleration. Some forces in y. Y is over here, so mg cosine theta minus n. Okay, and then there's only acceleration in the x direction, so ay is 0. And if it rolls without slipping, this acceleration is related to this acceleration, like that. So we have this equation, so we have these 4 equations. Okay, so let's solve for the acceleration. So let's see, I can use 1, 2, and 4. Okay, so I'm going to solve, I'm going to put this here. Let me do that right now. Okay. So RFS equals I alpha, but alpha is AX over R. And then let me move this R over here. Okay, so now I have an expression for static friction, which I'll substitute right here into equation 2. Okay, so equation 2, mg sine theta minus Fs, which is I ax over r squared, equals max. And I want to solve for that acceleration. Right, so I'll just pick this up, move it on that side. Max plus I over r squared ax. So then I can factor, so m plus I over r squared ax. And then I can just move that in the denominator. So ax equals mg sine theta over m plus I over r squared. Okay, so what does that mean? The moment of inertia shows up here in the denominator. And then what does that mean? Let me clean this up a little bit more. Let me divide numerator and denominator by mass. So that, and then over here. So let me clean that up. Okay. And then again, the moment of inertia is in the denominator, which means the larger it is, the lower the acceleration. So higher moment of inertia, slower acceleration. Let's go back to our table over here. So for example, a solid sphere, 2/5 mr squared. 2/5 is like 0.4. Right? Or a thin spherical shell. So if you, instead of solid, you hollow it out, that's 2/3. Right? So then solid sphere, hollow sphere. But then let's say it's like only partially hollow, then it'll be somewhere in between these two numbers. Versus, for example, a solid cylinder, 1/2 mr squared. Or you completely hollow it out, so then it's a hoop, infinitesimally thin hoop, then it's 1. Right? But then say it's like this, partially hollowed out. See, it's in between, so it's in between these two numbers. So then a hoop has the largest moment of inertia, so it would have the slowest acceleration. And then something like a solid sphere has the smallest moment of inertia, so it would have the highest acceleration. Okay, let's now make note of all of these have mr squared, but then just some number in front of it that's different. What if I just call that some variable x? So I'll say the moment of inertia, I, this one over here, is just some x mr squared. Right, x, where x is 1 for a hoop, half for a cylinder, 0.4 for a solid sphere. And then see how this simplifies like that? Like that. For x being that coefficient, which depends on the shape. Okay, so for your experiment, the goal will be you figure out this coefficient. So let's say you find a ball, a solid sphere, a hollow sphere, and a cylinder. It's not going to be exactly perfect where it's going to be 1 and 0.5 and 0.4. So you find the experimental value for that coefficient. So then how you would do it, put it at the top of your ramp, at rest, let it roll down, and then you need to know this distance for your ramp, you need to know this angle for your ramp, and then you time how long it takes. Just like the last time, you could video record it and then count the frames. And then, if we go a little bit further with the computation, so notice that this is constant, which means we can use kinematics for constant acceleration, like this. Okay, and then if we start at, let's say, 0, and then it goes to some distance d, so I'll call this d, and I'll call that 0, 0. And if we're starting at rest, this is 0, so this is 0. Starting at rest is 0. 1/2 ax t squared. Ax is this. Let me just substitute that right there. G sine theta over 1 plus x. So take a look at this. You just simplify, right? Simplify this. I'll leave it to you. And then if you take a look at it, if you measure the distance d, you measure the angle, you already know g, measure the time, the only unknown is this coefficient we're looking for. Okay, and then you would do 10 trials for each of your objects, and then you take the mean and the standard deviation. The mean value is what goes here for that time you measured. Okay, let me show you some examples. So let's get this picture here. Okay, so here I have my ramp set up. So you would do this one object at a time. So then you can record, so you can figure out the time. But then I just wanted to show you kind of an overview of what to expect. So I set up this ramp. Initially I was going to just use a table like this, and then I put books under one leg of the table like this. So then it's at an angle, and then I just put objects to roll. But the table is a little bit shiny for the purpose of recording so you can see this video. So I just looked for something with a kind of dull finish. So this is, I don't know what it's called. It's like, my daughter does ballet, so this is the bottom part of some stand where you can stand on it and do turns, like pirouettes. So the bottom side of this thing is slippery, and then what you see, this black side, is like the grippy part, so it doesn't slide on the ground. And then here I have a can of garbanzo beans, so that's supposed to be like a solid cylinder. It's not exactly, but because there's a little bit of air in there, so I would expect it somewhere in between a solid cylinder and a hoop. So a little more than 0.5, I would guess. And then that red ball is a solid sphere. It's definitely solid. And then the orange one is a thin shell, but not infinitesimally thin. So I expect it to be somewhere between these two values, like 0.6 or something. And then I grab the stick to make sure that they all go at the same time. And I had this video you're watching is playing at 30 frames per second, but I recorded this footage at 120 frames per second. So this playback is at a quarter speed. So here I release them all at the same time. So you can see the solid sphere has the highest acceleration, and then the cylinder and the thin shell were really close. So here's another trial. And I did a lot of trials. So for this particular orange thin ball, and then that can, the cylinder, it was always pretty close. Okay, now here's another setup. So this is the can again, because it's easy to see on the video. And then that like blue and purple thing is like my kids, kind of like Lego. They look like cups that stack. So it's kind of, if you took a solid cylinder and a hoop and kind of glued them together. So I expect the moment of inertia to be somewhere in between 0.5 and 1. And then the can of beans is going to be a solid cylinder. So my hypothesis here is that the can is going to win, is going to be faster. Okay, so there you go. And then my last setup, I just found the same can and then empty toilet paper roll, which I expect to be really close to 1 mr squared, like an actual hoop. So I expect that one to be really slow for the acceleration. So here it goes. And it's not perfect. It's not perfectly round, so it's kind of wobbling its way down. But definitely you can see how that acceleration is really slow. And then for the data, it's because the time here would be longer. Okay, so for this week, just set up your ramp, find your 3 to 5 objects, run 10 trials each, and then make sure you measure the distance and the angle. So then you have 10 trials to jot down the time, put it all in a table. And then next week we can go over again in better detail these computations and then how to format the lab report. Okay, so let me know if you have any questions. You can put those in the forum. Other than that, I'll see you in the next video.